Video, we're going to describe how the values of A, H, and K can transform a parent graph. And so far in this course, we've looked at four main types of parent graphs: the constant, linear, absolute value, and quadratic. And for all four of these, you should know how to create a table of values and create an accurate graph for them. And what we're going to do is we're going to explore what changes we can make to these parent graphs, how we can transform them. So our key vocabulary term for today is the word transformation. And a transformation changes the size, shape, position, or orientation of a graph. So everything that we look at is going to do one of these four things: change the size, shape, position, or orientation. Now, the values for A, H, and K transform all of the parent graphs in an identical way. So we looked at these when we were in algebra class, and we talked about A, which is the value that is multiplied out in front of the parentheses or the absolute value brackets. And A has a very specific change that it makes on a parent graph. And luckily, it's the same change consistent through all parent graphs. So what it does to the linear graph, it does the same type of thing to the absolute value graph and the same type of thing to the quadratic graph. Then we have our H values, which are inside of the parentheses or the absolute value symbols with X. So they're along there with X, they're being added to X. And H does a very specific transformation as well. And luckily, again, it's consistent between all of the types of graphs. And then finally, we have the K value, which is being added on the outside of the parentheses or the absolute values. And again, it is consistent. It's the same type of change. So we're going to study the absolute value graph in detail, and we're going to look how these transformations transform the absolute value graph. But what we discuss about A, H, and K is consistent and can also apply to the linear and the quadratic graphs as well. A, H, and K do the exact same thing to all three types of graphs. So what we're going to do is we're going to explore how changing the value of A actually transforms this parent graph of the absolute value. So we're going to pull up Desmos here. And what you'll notice is that in red behind all of this is our parent graph. It's the generic y equals the absolute value of x graph. And then over the top of it, I'm putting a blue graph that has values for A, H, and K with a slider. So I'm going to slide A, H, and K around, and we're going to see what happens to this graph as we alter A, H, and K. So here you'll see by default A is currently set to 1. That's because when you multiply, multiplying by 1 is what keeps that graph consistent. So A is by default 1 unless you change it. So from here, we're going to change A, and we make A, let's say, 2. So what I'm noticing here is this blue graph is getting skinnier and skinnier and skinnier. And essentially what's happening is this graph is actually becoming taller. What we're doing as we change A is we're multiplying all of the points that are on this red graph, all of the y values on this red graph, and in this case right now we're multiplying them by 6. So what we're doing is we're making that graph 6 times as tall. So when A is something like 6, it gets very, very skinny and then gets very, very tall as a result, and that's called a vertical stretch. Now, when we make A something else, let's say something between 1 and 0, you'll notice that A starts to get very, very flat. So right now, A is equal to 0.2. What's happening to all of the y points on this graph in red is we're taking these y points and we're multiplying them by 0.2. So essentially, this graph in blue right here is about 0.2 times the height of A. So it's only a fifth of the height there because 0.2 is equal to a fifth. So we've shrunk it down, and this is called a vertical shrink. Now from here, if we make A negative, you'll notice that A flips over. So anytime A is negative, it flips over the graph, and that's a vertical flip. So what can happen with our A value is we can have a vertical stretch, a vertical shrink, or we can have a flip. Now, what's also kind of interesting, so let's set A equal to 3 here for a second. You'll notice that this graph is in fact stretched. So it's stretched up to be 3 times its height. If I change A to be -3, it's the exact same graph down below here. So A not only can have a stretch factor where it stretches, but it can simultaneously stretch and flip. So you have to be on the lookout for that. A can actually have two things going on. It could stretch and flip, it could shrink and flip, or it could just stretch or just flip or just shrink. So you got to pay close attention to that as you're working with these A values. So we're going to go back to our slides here and we're going to summarize that. So it says absolute value of A. That's basically saying A is something like 6 or -6 or 5 or -5. It's some number that is more than 1 unit from 0. If this happens, we are going to have what is called a vertical stretch. Is that there? I'm not spelling vertical very well. So this is a vertical stretch. So that means the graph is going to get taller in some sense. It's stretching it up to be a taller graph. Then if A is something that has a distance from 0 that's more than 0 but less than 1, so something like 0.5 or -3/4 or 0.2, something that is between 0 and 1 units from 0, this is going to be called a vertical shrink. And that's going to make the graph shorter. It's going to make it wider. It's kind of going to make it fatter because it's going to shrink it down. And then lastly, if A is negative, we're going to have what is called a vertical flip. And it's going to flip the graph entirely over that x-axis there. So that's how A impacts our parent graph. And that's how it impacts all parent graphs, whether it's quadratic or absolute value or linear. So next thing we're going to take a look at here is the k value. So we're going to set A back to 1. And now we're going to start manipulating the k value. And you'll notice that k by default is 0 because it's something we're adding on. And so as we change k, I want you to notice what happens to the graph in blue. So notice that as k becomes 3, look at its location. 4, look at its location. Hopefully you're noticing that all that's happening to this blue graph is whatever k is, that's how the graph moves up and down. So if k is a positive 2.2, it means that graph in blue moved up 2.2 units. If k is a negative 2.6, it means that that graph moved down 2.6 units. So all that k value does as it changes is it changes where the graph is vertically, and this is called a vertical shift. So if we go back here to our notes, we're going to note that k is what is called a vertical shift. So k is how we change vertically, and if k is positive, the parent graph moves up that many units. And if k is negative, the parent graph moves down that many units. So A causes some size changes. It causes it to stretch and shrink and flip. And then K actually moves the graph around vertically. It shifts it around in a vertical fashion. Now, the last thing we're going to look at here is we're going to look at H. So H, you'll notice by default is set to 0. So it's something we add inside of the absolute value or inside of the parentheses in the case of the quadratic for these functions. So it's right inside of there with X. And if we change H, I want you to notice very carefully as H becomes positive, look at where it's going. What I notice as H becomes positive is it moves to the left, which is the negative direction. And if H becomes negative, it moves to the right, which is the positive direction. So H is a horizontal shift. It's a horizontal movement, but H works the opposite of what I expect it to. If H is something like a positive 5, it goes to -5. If H is something like a -3, it goes to +3. So you have to pay attention closely how it is shifting around the graph. So H here is what is called a horizontal shift. So it's a horizontal movement. And sorry, that's a bad F there. We'll try that again. horizontal shift. And I want you to make a note here that H is the opposite of what we expect it to be. So if H is positive, it's going to move to the left, which is the negative direction. And if H is negative, it's going to move that many units to the right, which is the positive direction. So just make note of that H moves the opposite of what we expect. So those are our 3 transformation types that we learned back in Algebra 1, and we're going to use those as we study these parent graphs a little bit more deeply.